Okay, so where we're at now is that we need to normalize this function. We need to divide this function by its integral over all values of w in Rd. So there's two key terms here. There's this quadratic term in w, and there's this linear term in w. And so already from this we are able to conclude that the posterior distribution is a multivariate Gaussian. So in the next slide I'll go through some steps for actually doing this. But first, why is it that we can make this conclusion? So in order to solve Bayes' rule, we're allowed to multiply and divide this term by anything that doesn't involve w. So we can multiply it by something or divide it by something not involving w, such that we know that the result integrates to 1, and we've solved the problem. So we know that a Gaussian has this form in the exponent. We know that the Gaussian has minus 1/2 times this term in its exponent. And so what we can do is complete this square by adding terms that don't involve w in order to get this quadratic to be written in this form. So in other words, let's compare a Gaussian distribution with what we have. So here's what we have so far. We want to divide this term by some number z in order to have a probability distribution. So we want to find the value z such that this function integrates to 1. And on the other hand, we know that a multivariate Gaussian with mean mu and covariance sigma has this form. So what I've done here is actually multiply out this quadratic term from this slide. So we know that a Gaussian looks like this with mean mu and covariance sigma. Here's where we're at right now. We want to find this value of z that makes this function integrate to 1. And so immediately we're able to conclude that if we define this for this Gaussian, if we define sigma inverse to be equal to this, and we define sigma inverse times mu to be equal to this, so we plug in this term for sigma inverse mu here, we plug in this term for sigma inverse up here, which means we have to do something clever here. We have to say mu transpose sigma inverse times sigma inverse mu. So we plug the inverse of this in here, and we plug this vector in both here and here. Then we'll immediately find that if we set z to be equal to this, that these two are equal to each other. And so this is just a quick way that we can calculate the posterior as being Gaussian without actually ever having to try to solve this integral over w. We can say, for z, plug in this, and then solve and find that we can simplify the result to be a Gaussian with covariance equal to the inverse of this, and mean equal to, and the inverse covariance times the mean equal to this. In other words, what we can say is that the posterior of w, given data y and x, is a Gaussian with mean equal to this and covariance equal to this. And again, if we write out this function where we plug this in for the covariance and we plug this in for the mean, we expand everything out, we'll find that we can go back here and it's equal to this function divided by this constant with respect to w. So in other words, a Gaussian with mean and covariance set to be equal to these two things is proportional to this function. We simply need to divide it by some constant with respect to w. Let's look at a couple of interesting things about this. First, notice that the mean solution, the solution for the mean of the posterior distribution, is equal to the map solution. So if we use Bayes' rule to calculate a posterior distribution of w, the mean is going to be equal to the map solution, which we also know is equal to the ridge regression solution. But now we have a covariance, sigma, which captures our uncertainty about W in a way that's the variance of the ridge regression and least squares solution also captured some uncertainty of W. But now we actually have a functional distribution that we can work with. So we can actually give densities and calculate probabilities that we couldn't do when we calculated these variances.